Right, welcome to the class. Today we're going to have a look at the second lesson of chapter 7. Electric fields, potential difference, and electric potential. So if you have typed a letter on a computer, heard musical tones from a cell phone, or even just pressed the flow button in an elevator, then you have applied an electric force. In fact, almost everywhere you go, you will find a device that, in one way or another, uses electric fields. An electric field is what causes electric force. At the dentist office, the X-ray machine uses an electric field to accelerate electrons as part of the process for producing X-rays. At coal-burning power plants, electric fields in smokestack scrubbers remove soot and other pollutants before gases are released into the air. Even when you are speaking into a telephone or listening to the other person on the line, electric fields help convert sound to electricity and back to sound again. The liquid crystal display, or LCD, is a device that uses electric fields. Nearly all computer monitors, digital cameras, and smartphones use LCDs for their visual components, as shown here in figure 1. So LCDs consist of liquid crystal between two transparent sheets of glass or plastic with a thin conducting material on the outside of the sheets. An electric field across the crystal causes its molecular arrangement to change, so that light passing through it is made either lighter or darker, depending on the design of the device. In this way, small changes in the electric field can make nearly any pattern appear on the LCD. So let's have a look at the properties of electric fields. We can describe the electric field between a pair of changes using Coulomb's law, but there is another way to describe electric forces. Suppose there is a single isolated point charge that is far away from any other charges. This charge produces an electric field, a region in which a force is exerted on an electric charge. The electric field is smaller to the gravitational field near the isolated mass, as discussed in previous chapter 6. So, were another charge to enter this field, the electric field would exert a force on it, much as a gravitational field exerts a force on a mass. The electric field has both magnitude and direction. So electric field is a vector, which is usually denoted by epsilon. Consider a particular point in space where there is a uniform electric field epsilon, which is shown here in figure 2. A point charge or arrangement of several charges may have produced this field. A charge Q at this location in the field will be affected by the electric field and experience an electric force, which is given by this formula. The electric force Fe equals Q times the electric field strength, which is denoted by epsilon. The electric force Fe is thus parallel to the electric field epsilon, with direction depending on whether the charge is positive or negative. So the charge Q1, or the charge affected by the field, which is shown here in figure 2, is called a test charge. As a convention, physicists use a positive test charge to determine direction. By measuring the force on a positive test charge, you can determine the magnitude and direction of the electric field at the location of the test charge. Since we are working with a positive test charge, Q1, the electric field in the same direction as the force that test charge experiences. If Q1 happens to be a negative charge, then the direction of the electric field is in the opposite direction of the force that the negative charge experiences. The units for electric field can be determined from the equation relating electric force to electric field. Force is measured in newtons, right? And charge is measured in coulombs, which is denoted by C. So the electric field is expressed in newtons per coulomb. The electric field epsilon also relates to Coulomb's law for electric force. Coulomb's law for electric force allows us to calculate the electric field using the amount of charge that produces a field, Q2, and the distance of the field from the charge, which is usually denoted by R. As the example, calculate the magnitude of the electric field at a distance R from a charge Q2. The test charge is once again denoted by Q1. So according to Coulomb's law, the electric force exerted on Q1 by Q2 has a magnitude of Fe equals KQ1 Q2 over R squared, right? Inserting this expression into the equation relating electric force to the electric field gives the result. So QE equals Fe, Q epsilon equals Fe. Then we have Q epsilon equals K, Q1, Q2 over R squared. So in this equation, because Q equals Q1, so we get the electric field strength S epsilon equals K Q2 over R squared. So this is actually the magnitude of the electric field at a distance R from a point charge Q2, which is given by this formula here. The direction of the electric field, epsilon, lies along the line that connects the charge producing the field, Q2, to the point where the field is measured. The direction of the electric field is determined by a positive test charge. If Q2 is positive, then a positive test charge will be repelled away from it, and thus the electric field points in the direction away from a positive charge. If Q2 is negative, then a positive test charge will be attracted toward it, and thus the electric field points in the direction toward a negative charge. As a result of the direction of the electric field, depending on the type of charge and the location in relation to the charge. Usually, we do not include the signs of charges in the equations to avoid implying a direction. Okay, do you have any questions? All right, no questions. Let's have a look at an example. How we can calculate the electric field due to two-point charges in one dimension. So here in this example, we have two-point charges which are 45 centimeters apart, which is shown here in figure 3. The charge on Q1 is 3.3 times 10 raised to the power of -9 coulombs. And the charge on Q2 is -1.00 times 10 raised to the power of -8 coulombs. So there are two questions you need to answer. First, can you calculate the net electric force at point P, which is 27 centimeters from the positive charge on the line connecting the charges? Second, a new charge of positive 2.0 times 10 to the power of -12 coulombs is placed at P. Can you determine the electric force on this new charge? Okay, I'll give you 5 minutes to consider this question by yourself, and then we'll have a look at the solution together. All right, have we finished? Okay, let's have a look at the solution together. Okay, so note that the electric field is a vector, right? Net electric field at point P should equal the vector sum of the electric fields from the charges producing the fields. So we can use the equation, the electric field strength, epsilon equals kq over r squared, to calculate the electric field strength for each of the from each of the charges Q1 and Q2 at point P, right? Then determine the direction of each field based on the signs of the charges. Then combine the two vectors to calculate the net electric field. Okay, so first we can calculate the magnitude of the electric field at distance r1 from the charge Q1 and determine the field direction. First, the magnitude of the electric field strength due to Q1 is kq1 over r1 squared. Put all the values in, we have epsilon 1 equals 4.070 times 10 raised to the power of 2 newtons per coulomb. Since Q1 is a positive charge, the electric field on a positive test charge at P will be directed away from Q1. Therefore, direction of the electric field epsilon 1 should be pointing to the right. To use the same method, we can also calculate magnitude and direction of the electric field due to point charge Q2. Again, put all the values in. We have electric field due to Q2 at point P is 2.775 times 10 to the power of 3 newtons per coulomb. Since Q2 is a negative charge, the electric field on the positive test charge at P will be directed toward Q2. Therefore, the electric field at point P due to Q2 is also pointing to the right. Therefore, the net electric field at point P due to point charges Q1 and Q2 is the vector sum of the two electric fields, epsilon 1 plus epsilon 2, which gives us 3.2 times 10 to the power of 3 newtons per coulomb. Any questions? Okay. Then if we know the electric strength at this point P, then for any given point charge at this point, we should be able to find the net electric force due to the electric field strength here, right? So we can use the equation Fe equals Q times epsilon to calculate the net electric force for the test charge Q at point P. So Fe net equals Q epsilon net at point P. Again, you know Q and also epsilon net. Put all the values in, we have the net electric force on the new charge at this point is 6.4 times 10 to the power of -9 newtons. And the direction is to the right, because the charge is positive, right? So the electric force should be directed to the same direction with the electric field. So the final statement is electric force acting on a new charge at point P is 6.4 times 10 to the power of -9 newtons to the right of point P. Any questions? No? All right, then let's have a look at another problem in two-dimensional space. So in this question, we have 2 point charges which are arranged as shown here in figure 4. Q1 equals 4.0 times 10 to the power of -6 coulombs. Q2 equals -2.0 times 10 to the power of -6 coulombs. and R equals 3.0 centimeters. So given this configuration, can you calculate the magnitude of the electric field at the origin? Okay, I'll give you 5 minutes to have a look at the question by yourself first. So note that this question is a two-dimensional space. So you should apply the vector addition in 2D space, right? All right, let's have a look at the solution together. So note that at the origin point, the electric field due to Q1, because Q1 is positive charge, right? So at the origin point, the electric field due to Q1 should be pointing this way, right? Then the electric field due to Q2 should be pointing this way. So according to the vector addition, the net electric field strength should be this vector here, right? So we can use this right triangle to find the magnitude of this side, and then first calculate the magnitude of the electric field due to Q1 and then due to Q2, and use the Pythagorean formula. The magnitude of the net electric field strength should be the square root of the sum of the epsilon1 plus epsilon1 square plus epsilon2 square, right? Okay, so following this logic, first we can calculate the magnitude of the electric field along the horizontal and vertical directions. The electric field of Q2 has only an x component. Therefore, the electric field epsilon x equals kq2 over r squared, right? Put all the values in, we have the x component of the electric field at the origin is 1.998 times 10 to the power of 7 newtons per coulomb. Then the electric field of Q1 has only a y component. Therefore, the y component of the electric field at the origin point equals kq1 over r squared, which is 3.996 times 10 to the power of 7 newtons per coulomb. Then use the magnitude of the net electric field at calculate the magnitude of the net electric field at origin, which is the square root of epsilon x net square plus epsilon y net square. And this gives us 4.5 times 10 to the power of 7 newtons per coulomb. This question does not ask us to find the direction, so you can stop here. Then makes final statement. The magnitude of the net electric field at the origin is 4.5 times 10 to the power of 7 newtons per coulomb. Okay, any questions? All right, no questions. Let's have a look at another topic, which is about electric field lines. So an electric field exists in a region around a charge. The field and its properties can be represented with electric field lines. These electric field lines can help us determine the direction of the force on a nearby test charge. As was stated earlier, electric fields point away from positive charges and towards negative charges. This convention is based on using a positive test charge to determine direction. To show what the electric field would look like around a positive point charge, we can draw electric field lines that extends radically outward from the charge, as shown here in figure 6a. For a negative charge, the field lines are directed inward towards the charge, which is shown here in figure 6b. As you may expect, the electric field lines are parallel to epsilon, and the density of the field lines is proportional to the magnitude of the electric field epsilon. In both parts of figure 6, the field lines are densest near the charges. In both cases, the magnitude of epsilon increases as the distance to the charge decreases. According to Coulomb's law, the force between the 2-point charges varies as 1 over r squared, where r is the separation between the two charges. In a similar way, the electric field produced by a point charge also varies as 1 over r squared. The electric field thus obeys an inverse square law, just as the gravitational force does, which is shown here in figure 7a. The magnitude of the electric force is proportional to the density of field lines. That is, the number of field lines per unit area of space at some distance r from the charge or charges producing the field. For a given point Q, which is shown here in figure 7b, the density of field lines decreases farther away from the charge. The field lines from Q spread out through a surface area. Therefore, the number of field lines per unit area A, and thus the respective strengths for the electric field and electric force should decrease as r squared increases. Another interesting aspect of the electric field relates to the question of action at a distance. So how do 2-point charges that interact through Coulomb's law know about each other? In other words, how does one charge transmit electric force to another charge? In terms of electric field lines, every charge generates or carries with it an electric field through which the electric force is transmitted. So let's have a look at another concept, which is electric dipoles. So consider the 2-point particles with equal but opposite charge in figure 8. Charges with negative Q and positive Q, where Q is a positive magnitude of the charge, are separated by a small distance r. This charge configuration is called an electric dipole. So basically, electric dipole is a pair of equal and opposite electric charges with centers separated by a small distance. So the two charges in an electric dipole give rise to a more complicated electric field than the one associated with one single electric charge. This is because electric fields around the individual charges can interact most strongly with each other at close distances, such as those that are similar in size to the dipole separation. Initially, the fields at the negative charge radiates inward towards the charge, and the fields at the positive charge radiate outward from the charge, which is shown here in figure 9a. As the fields extends into the space around the other charge, they can interact with each other, producing field lines that bend toward the other charge, which is shown here in figure 9b. So notice that along the vertical axis midway between the two charges, the electric field is parallel to the line connecting the two charges. This remains true along the vertical axis at all distances from the dipole, although the magnitude of the electric field decreases at distances that are farther away from the dipole. Direction of this electric field always points from the positive charge to the negative charge. Although the field lines of a dipole merge at the midpoint, field lines do not cross. Instead, the cumulative effect, or the vector sum of the electric fields from both charges, produces a net electric field. That net electric field is represented by the electric field line. Okay, so now let's consider another arrangement of charges slightly different from an electric dipole. In this case, as shown here in this figure, a positive charge, positive Q, replaces the negative charge, negative Q, so that the two charges are equal and alike. Now the electric field lines extends outward from both charges. Instead of the field lines from a positive charge merging with the lines from a negative charge, the lines from similar charges do not connect at any point. This arrangement produces a disc-shaped region of zero electric field everywhere around the midpoint between the two charges. Notice that farther away from these charges, the field behavior starts to resemble that of a single charge. That is, the field lines appear to be radiating from a single point charge. This makes sense because at a large distance from the two charges, the separation between them is not noticeable, and both charges have the same sign. Midway between the two charges, there is a gap where there are no field lines. This is expected because the vector sum of the two electric fields from both charges is zero at the midpoint. Note that this electric field pattern would be the same if the two charges were both negative. Difference would be in the direction in which the field lines were pointing, but not the shape of the combined fields. Okay, finally, let's consider a dipole-like arrangement of two charges that have different magnitudes and signs, which is shown here in figure 11 here. If the positive charge positive Q is replaced with a charge positive 2Q, the symmetry of the dipole fields is altered. This is because the number of field lines for each charge is proportional to the magnitude of that charge. The number of field lines leaving the positive charge is therefore twice the number of field lines meeting at the negative charge. So half of these lines converge on the negative charge, while the other half just emanate outward, as if there were only one charge, positive 2Q. At large distances, where R is much greater than the charge separation, the electric field radiates outward as it would for a charge of positive 2Q. So the field line pattern for unequal and opposite charges includes regions near the charges where the density of field lines becomes very high. Note that this does not mean that electric field is stronger in these regions. The electric field is still strongest along the line connecting the charges. Electric field patterns can become very complex, but many simulations exist to show what the electric field would look like in a multi-charge system. Okay, next let's have a look at uniform electric fields. So far, we have learned about electric fields that vary with distance from a charge. In this case of a dipole, for instance, the strength of electric field varies with a number of charges, their placement, and distance from the charges. A different electric field arises from a different type of dipole. Instead of point charges, suppose we have two parallel planes of charge. As with the dipole, one plane has a positive charge and the other plane has a negative charge. In both cases, the charge spreads uniformly along each plane. Just as the electric field along the line connecting two unlike charges extends straight from the positive to the negative charge, The electric field between the planes of charge extends from the positive plane of charge to the negative plane and is uniform. These field lines are straight, parallel to each other, and perpendicular to the planes of charge. At any location between the plane, the electric field has the same magnitude and direction. Outside the plane, though, the vector sum of the electric fields from all the individual charges in the two parallel planes yields a value of 0. This description of planes of charges involve infinite parallel planes carrying infinite amounts of charge and thus do not exist in real-world scenarios. However, we can create a close approximation by using two large conducting plates charged by dry cells. These plates are parallel and carry equal and opposite charges. As long as the separation between the plates is much smaller than their surface area, the electric field between the plates remain uniform. In fact, except near the edges of the plates, the magnitude of the electric fields depends only on the amount of charge, the area of the plates, and the material between the plates. Okay, so next, let's have a look at the electric field of Earth. The energy from the sun bombards Earth's upper atmosphere. Some of this energy scraps electrons from atoms, leaving a region of positively charged ions and free electrons, right? Some of the electrons recombine with the ions, but others travel into space and the other region of the atmosphere. This region, approximately called the ionosphere, therefore has a positive charge and is able to conduct electricity. In contrast to the ionosphere, Earth's surface is more negatively charged. Both areas tend to stay charged so that a permanent electric field exists throughout the atmosphere. Near Earth's surface, when the sky is clear of storms, the electric field has an average magnitude of about 120 newtons per coulomb. This electric field varies seasonally, but the greatest and most sudden change occurs during thunderstorms, when the atmospherical electric field can reverse direction. Cloud to ground lightning, which often accompanies these storms, is both very common and potentially very destructive. So it's essential that scientists understand how Earth's electric field changes during storms and what field conditions are likely to result in lightning strike. So one device called an electric field mill, or just field mill, is widely used to measure Earth's electric field. A field mill makes use of the uniform electric field between the two parallel conducting plates and detects changes in the field strength at a given location. The design of field mill incorporates two circular conducting plates, which is shown here in figure 13. The conducting plate at the front of the mill is the sensor plate. This part of the mill is exposed to the atmospherical electric field. A set of motor-driven rotating shoulder blades. The mill exposes the sensor plate for a short time and then blocks the plate from the electric field for an identical length of time. During exposure, the plate becomes charged. During non-exposure, an analyzer circuit measures the electric field between the charged sensor plate and the uncharged detector plate. This process repeats continuously, providing information about variations in the field strength of Earth's electric field over a given time interval and in a particular region of the atmosphere. The field mills have fairly simple designs and generally perform reliably. Although often set up in permanent positions on the ground, field mills located in balloons and aircraft measure field changes at different elevations. Field mills are used in cases where lightning could do extreme damage, as such to spacecraft before launch. Okay, next, let's have a look at a device called electrostatic precipitators. During the industrial age, heavily polluted air resulted from the smoke pouring out of chimneys and smokestacks. Most of these emissions, called flue gases because they passed through the flues of chimneys, consist of gases such as nitrogen and carbon dioxide, most of which are clear substances. However, tiny particles of carbon, sulfur compounds, and dust produced by various chemical processes and combustion combined with gases. These particles give the air its smoky appearances. Today, industrial processes continue to pollute our air. Air containing polluting gases leads to many environmental concerns, such as climate change and acid precipitation. Acid precipitation is also to harm both plants and aquatic life. The polluting gases also affect the respiratory health of not only the people who live nearby, but also those who live where the prevailing winds tend to push the gases. In recent years, devices called electrostatic precipitators have reduced the number of these particles released into the atmosphere. Electrostatic precipitators also use electric fields to remove extremely small particles of soot, dust, and ash from flue gases and other emissions produced by combustion, smelting, and refining. So the exact arrangements of different electrostatic precipitators can vary, but the basic principle is the same in all of them. In the design shown here in this figure, figure 14, the flue gas and particles it contains pass between a grid of negative charge, conducting wires, and conducting plate carrying a positive charge. The wires transfer electrons to the various particles that come into contact with the wires. The wires transfer electrons, making the particles negatively charged, and the electric field between the wires and the plates is about 10 to the power of 6 newtons per coulomb. So the force drawing these negative charged particles toward the positively charged plates is very large. Shaking the plate from time to time loosens the particles that accumulate on them. A storage or collection hopper below the precipitator collects this refuse. Repeating the procedure of passing the flue gas through several series of plates and wires can remove about 99% of the various particles from the gas. So some of these devices used for home air purification as well. They use the same basic principles of electrostatic precipitators. However, the results from these air cleaners have been mixed, partly because of the comparatively low levels of particles in household air, and partly because the electric fields are not as strong as in industrial precipitators. Okay, next, let's have a look at electric fields in nature. The electric fields are also produced by animals. These fields are often weak and produced by ordinary actions, such as motion in the muscles. Some animals have organs that can detect and respond to these weak electric fields. The hammerhead sharks, for instance, detects fields as low as 6 newtons per coulomb in fish. that hide beneath the sand or in tunnel shelters along shallow ocean bottoms. The hammerhead shark swim close to the sandy ocean floor, which is shown here in this figure. It preys on goby, small fish that hide in sand-covered holes. The goby produce electric fields from muscular movements of its fins or gills. Although the shark cannot see the goby, it can detect these electric fields up to 25 centimeters above the sand. Having detected the goby, the hammerhead shark swims in a figure 8 until it pinpoints the location of the greatest electric field strength and then catches and consumes the goby. Okay, so this is the first half of today's lesson. Can take 5 minutes break. And then we'll have a look at the second part of today's lesson. Potential difference and electric potential. Okay, now let's have a look at section 7.4. Potential difference and electric potential. So in the first half of this lesson, we have learned how two parallel charged surfaces produce a uniform electric field. From the definition of an electric field as a force acting on a charge, it follows that for a given uniform electric field charge and particle mass, the particle undergoes uniform acceleration, right? Another way of thinking about the physics of this situation is that the electric field does work on the charged particle. This view works well if the charge stays constant, but in reality, the work done by the field varies with charge. What if, instead of describing the electric field in terms of force per charge, we express it in terms of energy per charge? As it turns out, we can describe the field in this way, as we'll learn this in the second half of this lesson. So no matter how we choose to describe the uniform electric field, its ability to accelerate charged particles with known conditions has proven useful to physicists and engineers. Devices such as particle accelerators, which can accelerate particles to speeds near the speed of light, can only work if the particles are moving in the first place. Electric fields cause initial motion of these particles by accelerating them. Particle acceleration is important in some everyday devices as well. Inkjet printers accelerate charged ink particles towards specific parts of the paper, which is shown here in figure 1. All television sets and computer monitors have cathode ray tubes. These tubes accelerate electrons toward a phosphor screen. Variations in the deflection of the accelerated electrons determines brightness and color of the screen. Okay, so let's have a look at the work and the electric potential difference. Recall that in a region of space where the electric field epsilon is constant, epsilon has the same magnitude and direction at all points. A point charge Q in this region experiences an electric force, which is denoted by Fe. Fe equals Q, the electric charge, times the electric field, epsilon. The force is parallel to epsilon, which is shown here in figure 2. So suppose this charge moves a certain distance, delta D, starting at point A and ending at point B. For simplicity, assume this displacement is parallel to the electric force Fe. According to the definition of work, which is usually denoted by letter W, the work done by the electric force on the charge is expressed as W equals Fe times delta D, right? The electric force does work on the charge and is independent of the path it takes from A to B. We can now define the electric potential energy, EE, which is the energy stored in the system that can do work W on a positively charged particle. From our studies of work and energy in previous unit, we know that the change in potential energy associated with this type of force is equal to negative W, right? Where W is the work done by that force. A more detailed explanation of meaning of the negative sign will be discussed in the later part of this lesson. So if the electric force does an amount of work W on a charged particle, the change in the electric potential energy can be expressed as delta E is negative W, right? Which is negative Fe times delta D. Combining this equation with equation relating force to the electric field, the change in electric potential energy when the charged particle moves from A to B in figure 2 is then expressed in this way. Delta E is negative W, right? Which is negative Fe delta D. Therefore, we know, on the other hand, we know Fe is Q epsilon, right? Therefore, delta E can be expressed as negative Q epsilon times delta D. So this equation here gives the change in the potential energy as the charge moves through a displacement delta D in the region where the electric field is parallel to the displacement. Note that the change in the potential energy depends on the starting and ending locations, but not the path taken. In figure 2, the displacement is along a line, but the charge may move from A to B along many other paths without affecting delta E. Electric potential energy is stored through the potential effect of the electric field on an electric charge. This effect is illustrated in figure 3A, where the charge Q is moved from point B to point A by an external force Fa directed to the left. So the force vector Fa results from some external agent, which could be your hand, for example. The electric force on Q points to the right, assuming that Q is positive. So the displacement is opposite to the direction of the electric force. The work done by the electric field on the particle is thus negative, right? Therefore, according to the electric potential energy equation, the change in electric potential energy must be positive. In other words, a positive amount of energy has now been stored in the system composed of the charge Q and the electric field. The energy came from the positive amount of work done by the external force Fa that moved the charge from point B to A. As the charge moves from A back to B, the process then is reversed, which is shown here in figure 3B. Now the electric field does a positive amount of work on the particle because the electric force and the particle's displacement are parallel and the change in the electric potential energy is negative. Energy stored in the electric field and particle system is now taken out of the system. This energy can appear as an increase in the kinetic energy of the particle when it reaches B. Potential energy becomes kinetic energy. Okay, do you have any questions? Not, let's use an example to illustrate this concept. Okay, let's consider this sample problem here. So suppose we have a charged particle moves from rest in a uniform electric field. For a proton, can you calculate the change in electric potential energy when the magnitude of the electric field is 250 newtons per coulomb and starting position is 2.4 meters from the origin and final position is 3.9 meters from the origin? B, calculate the change in electric potential energy for an electron in the same field and with the same displacement. C, calculate the change in electric potential energy for an electron accelerated in an electric field with the same magnitude, but opposite direction as in question A and B, and with a starting position of 2.4 meters from the origin and final position of 5.0 meters from the origin. Okay, I'll give you 5 minutes to consider this question by yourself, then we'll have a look at the solution together. All right, let's have a look at the solution here. For question A, we can use the equation for electric potential energy in terms of Q, epsilon, and delta T, right? So the delta EE, the change in electric potential energy equals negative Q epsilon delta D. Note that delta EE is a negative for a positive charge traveling in the same direction as epsilon. Thus, the sign of Q takes care of whether there's a gain for negative Q or loss for positive Q of electric potential energy. Note that we can include the sign of the charge because we are dealing with energy, which is not a vector quantity and does not have a direction. Okay, so delta EE is given by negative Q epsilon times delta D, right? Where delta D is D1, is D final minus D initial. Then put all the values in, we have delta EE is negative 6.0 times 10 to the power of negative 7 joules. So the change in electric potential energy due to the movement of the proton in the uniform electric field is negative 6.0 times 10 to the power of negative 17 joules. The negative sign indicates that the electric field loses potential energy by doing work on the proton. So in this question, you should be able to tell the electric charge on the proton is positive 1.60 times 10 raised to the power of negative 19 coulombs. Okay, just careful with the constant here. So in question B, you can use the same equation for electric potential energy. Delta EE is negative Q epsilon delta D. Note that we include the sign, again, we include the sign of the charge to determine whether there is a gain or loss of the electric potential energy. So in this question, delta EE is positive 6.0 times 10 to the power of negative 7 joules. Any questions? So the method should be the same, right? Except the signs here is different. Okay, in question C, note that the sign for the electric field is negative because the electron is accelerating in the direction opposite to epsilon. So we can use the same equation for electric potential energy. Delta EE is negative Q epsilon delta D. Again, put all the values in. We have delta EE is negative 1.0 times 10 to the power of negative 16 joules. Again, in such a problem, you should be able to tell that the charge on the electron is negative 1.60 times 10 raised to the power of negative 19 coulombs. Okay, then if you don't have any questions, let's consider another problem here. Question A, using the law of conservation of energy, can you calculate the speed of the proton in part A of the previous question for the given displacement? Still remember the previous question here. Just write this information given down onto your notebook and use this given information to calculate the speed of the proton in part A. For the given displacement, assume that the proton starts from the rest. Well, basically, it's due to the conservation of energy, the difference in electric potential energy is converted to the kinetic energy of the proton, right? Which is given by 1/2 times mv squared. So in question B, can you determine the initial speed of the electron in part B of sample problem 1, assuming its speed has decreased to half of its initial speed after the same displacement? Okay, you have 5 minutes. You have a look at this question. All right, let's have a look at this question together. So in question A, we know the law of conservation of energy states that total change in potential energy of the field and particle system, and the change in kinetic energy of the particle should equal 0, right? Which is denoted by delta EE plus delta EK should be 0. The kinetic energy of the particle is related to its speed v by the equation delta EK is 1/2 times mass m times v squared. So use this equation and equation delta EE equals negative Q epsilon delta D for the change in potential energy of the field and proton system. So we have the following relationship. So we can combine these equations. First, delta E plus delta EK equals 0. Second, negative Q epsilon delta D plus 1/2 times m times v squared is also 0. Combine these two equations give us the expression for the speed of the particle, which is 2.7 times 10 to the power of 5 meters per second. So the speed of the proton accelerated for a distance of 1.5 meters by an electric field of 250 newtons per coulomb is 2.7 times 10 to the power of 5 meters per second. Okay, second, for situations that do not involve an object at rest, the change in kinetic energy is given by the equation delta EK is 1/2 mf squared minus 1/2 m vi squared. Again, use this equation and equation delta EE is negative Q epsilon delta D for the change in potential energy of the field and electron system. By the law of conservation of energy, then we have the expression for the initial speed of the particle, which is square root of negative 8 Q epsilon delta D over 3m. And put all the values in, which gives us the initial speed of the electron before entering the electric field is approximately 1.3 times 10 to the power of 7 meters per second. Okay, have a look at this. All right, if you don't have any questions, let's have a look at another concept, which is called electric potential. Electric potential energy is a property of a system of charges or of a point charge in an electric field, where the field is created by other charges. In either case, this electric potential energy is not a property of a single charge alone. For this reason, the potential energy depends on the values of the charges and the electric field involved in this situation. This leads to a new quantity called electric potential, which is usually denoted by uppercase V. which is a measure of how much electric potential energy is associated with a specific quantity of charge at a particular location in an electric field. Based on this definition, we have the following relationship. The electric potential V equals EE over Q. EE is the electric potential energy. So basically, the electric potential is the potential energy per unit positive charge, right? For a given point in an electric field. Electric potential, or just potential in a convenient measure, is a convenient measure because it's dependent of the amount of charge at a particular location in the field. It depends only on the electric field strength at that location. For example, if you had 1 coulomb of electrons at a particular location in a uniform electrical field, you would possess a certain amount of electric potential energy. If you double the amount of electrons to 2 coulombs at the same location in the electric field, you would have double the electric potential energy. In both these situations, you would have the same electric potential. The SI unit for electric potential is volt, named in honor of the physicist Alexander Volta. The volt relates to other SI units in the following equations. 1 volt equals 1 joules per coulomb, or 1 Newton meter per coulomb. The volt is used in measurement of many electrical quantities. Note in particular that the units of volts per meter are equivalent to units of newtons per coulomb. The units for electric field strength. These equivalent units give you several different ways to express units of the electric field. The ones most commonly used are 1 volt per meter equals 1 Newton per coulomb. Another convenient definition relating to the electric potential energy is electric potential difference, usually noted by delta V. We return to the concept of the change in potential difference and the displacement of the particle. We can define the change in the potential, or potential difference, for a charge Q that moves between the 2 points. So delta V should equal delta EE over Q, right? For the case of a uniform electric field, the equation for electric potential difference becomes delta V equals delta EE over Q, which is delta V equals negative epsilon times delta D. So this relationship shows how a non-uniform electric field varies with a change in electric potential, that is, electric potential difference, and the change in position in this field. Epsilon equals negative delta V over delta D. So this equation states that the magnitude of the electric field is largest in the regions where V is large and changes rapidly with small changes in displacement. Conversely, the electric field is 0 in regions where V is constant. Notice that because of the negative sign in the equation, the electric field points from regions of high potential to regions of low potential, which is illustrated in figure 4. If we consider a circuit in which a battery is a source of electric energy, a positive test charge will naturally move from the positive terminal where a high potential exists to the negative terminal where a low potential exists. Since the electric field points from the positive to negative, the positive charge will also move in the same direction as the field. Conversely, electrons will naturally travel from a region of low potential to a region of high potential in the direction opposite to the direction of the electric field. So the relation between the electric field and the changes in the potential and position involves the component of the electric field that is in the direction parallel to the displacement delta D. The electric field is a vector. So if you want to determine epsilon in a particular direction, you must consider how the potential V changes for a test charge moving along the direction. With this equation and knowledge of epsilon, you can in principle at least calculate how the electric potential changes as you move from place to place within the field. Strictly speaking, this relation only holds for small steps, delta D, in a constant field. You can, however, combine the potential changes delta V for many such small steps to determine the change in the potential difference over a large distance. So in that case, you should use a small bit of calculus, right? Integration. The following tutorial will demonstrate how to solve problems involve electric potential. Okay, so let's have a look at a sample problem to illustrate this concept. Okay, so consider this question here. The cathode ray tubes in old television sets and computer monitors work in a way that is similar to certain parts in particle accelerators. Both devices accelerate particles in a similar way, using the uniform electric field between conducting plates. Looked at another way, the particles accelerate as they move through an electric potential difference. So question A, an electron leaves a negative plate of a cathode ray tube and travels toward the positive plate. The electrical potential difference between the plates is 1.5 times 10 to the power 4 volts. Using the law of conservation of energy and the definition of electric potential difference, can you calculate the speed of the electron as it reaches a positive plate in the cathode ray tube? Assume that the electron is initially at rest. The mass of an electron is 9.11 times 10 to the power of -31 kilograms. Okay, next, calculate the magnitude of the electric field at the distance of 15 centimeters, which is at the end of the cathode ray tubes. Okay, I'll give you 4 minutes to have a look at this question by yourself. Then we'll have a look at this together. Yes, Okay, let's have a look at the solution for question A. Okay, we know by the law of conservation of energy, delta EE plus delta EK should equal 0, right? On the other hand, we know delta EE is Q times delta V, and delta EK is 1/2 times m times Vf squared because initial speed is 0, right? So put all the values in, we have Vf equals the square root of -2Q delta V over m. Delta V is the electric potential difference. So Vf is approximately 7.3 times 10 to the power of 7 meters per second when it reaches the positive plate. Okay, next, let's consider question B. So we know the equation for electric field in terms of potential difference and displacement is given by epsilon equals negative delta V over delta D, right? In other words, the electric field strength is the electric potential difference per unit distance, right? And do not forget the negative symbol in front of delta V over delta D. So again, put all the values in. We have the electric potential, electric field strength is negative 1.0 times 10 to the power of 5 volts per meter. So the negative sign here indicates that the field extends from high to low potential. The electric field vector always points from regions of high volts to regions of low volts because epsilon is parallel to the direction that a positive test charge would move if it were placed at that location. Okay, now let's consider one last question before we end today's class. So we have a setup here. An electron moves horizontally with a speed of 1.6 times 10 to the power of 6 meters per second between two horizontal parallel plates. The plates have a length of 12.5 centimeters and plate separation that allows a charged particle to escape even after being deflected, which is shown here in figure 5. The magnitude of the electric field within the plates is 150 newtons per coulomb. Can you calculate the final velocity of the electron as it leaves the plates? Again, I'll give you 5 minutes to consider the question, and after that, we'll have a look at the solution together. All right, let's have a look at the solutions for this question. If you haven't finished, I'll leave the question to you after this class, okay? So the electric field is uniform in this question and direct downward between the plates. So the electric force acting on a proton is also constant and directed downward. A constant downward force means a constant downward acceleration on a positive charge, right? However, because the charge is negative, the acceleration must be upward. To calculate the magnitude of the final velocity, we can solve for each component of the velocity. Note that in the horizontal direction, the velocity is constant, right? Because there is no acceleration along the horizontal direction. And the accelerated upward component can also be calculated using Newton's second law and the principles in dynamics, right? As long as we can calculate acceleration due to the electric force, we can then decide the final velocity along the y-axis. Then use the equation VF equals square root of the x component squared plus the y component squared. Then we can find the magnitude of the final velocity. Also, because you know the x component and y component of the final velocity, you can also find the angle theta as shown here in this figure, right? Okay, so following this logic, first we can calculate the acceleration along the y-axis, which is ay equals QE over m. QE is electric force, m is the mass of the particle. So put all the values in, it's approximately 2.634 times 10 to the power of 13 meters per square second. Then we can calculate delta t. We know the initial velocity vi equals L over delta t, right? Therefore, delta t should equal L over the initial speed, which is actually the speed along the x-axis. So this gives us 7.812 times 10 to the negative 8 seconds. Then we can calculate the final velocity along the y-axis, which is vyf equals ay times delta t. And this gives us 2.058 times 10 to the power of 6 meters per second. Then we can find the magnitude of the net velocity using the Pythagorean theorem. So VF equals the square root of VXF squared plus VFY squared. And this gives us approximately 2.6 times 10 to the power of 6 meters per second. Then because we know the components along the x and y axis, we know theta equals arctangent VYF over VXF. And this gives us 52 degrees. So we know we can make the final statement like this. The final velocity of the electron is 2.6 times 10 to the power of 6 meters per second. And the direction is 52 degrees north of east, which is a theta here shown in this figure. Okay. All right, this is the end of today's class. Remember remember to review the reading material I gave you on Google Classroom, and please complete all the homework and submit them before the deadline on Google Classroom, okay? All right, I'll see you next time. Bye.